Okay, so lecture 33 is on statics. Statics, what does that mean exactly? What does the word static mean to you?
Still.
Still, not changing, right? So in a static situation, the sum of the forces, sum of the external forces, is equal to 0, which means that the acceleration is equal to 0. Nothing's accelerating, okay? Now that doesn't mean that nothing's moving, but if they're moving, they have to be moving at a constant velocity, okay?
All right.
So we're going to consider three problems here in statics. They all involve a mass being suspended from some kind of wire or string or rope or whatever you want to call it. So let's look at the first one, right? Here we just have a mass suspended from, say, the ceiling by some rope, okay?
Okay.
Now, the first thing that we do in problems like this is isolate the system that we're interested in, okay? And in this case, it's the mass, okay? So we draw a nice diagram. Let me do it like this, maybe. And we have to indicate where all the forces are. No, I'm going to do it like this. This is a mass M. And we'll say that here we've got the weight of the mass acting in the downward direction, okay? And you might recall that that would be equal to the mass times the acceleration due to gravity, but this is negative because it's in the negative direction. Well, actually, I haven't said what the direction is yet. Actually, let me, where my here is. I'm just going to pick up from there. So the first component is its weight, which is equal to the mass of the body, m, times the acceleration due to gravity.
All right.
And then we have a tension. That's from the rope or the string or the chain or whatever you want to consider it to be. And that's pulling upward on the mass. Okay, maybe this is a picture. Maybe it's a heavy block. Maybe it's an engine. Who knows? So now that we've got a nice picture, we need to put in a coordinate system, right? So let's put in an xy coordinate system with x in this direction and y in that direction. So that, of course, makes the weight a negative vector because it's acting in the downward direction, whereas the tension is acting in the upwards direction, okay? Now, you'll notice that there don't seem to be any forces in the x direction. So that makes this a particularly easy problem to solve. So for us, in this case, the sum of the external forces is just going to be the sum of the external forces in the y direction, okay?
Okay.
And so let's enumerate those now. We're going to have the tension plus the weight, and that is going to be equal to 0 because this is a statics problem. There's no acceleration, okay? And so that means that the tension is equal to minus the weight. But the weight we said was equal to minus mg, which means that the tension is equal to a negative times a negative is positive, m times g. Okay? I guess I could catalog that result over here. Okay? Makes sense? Pretty straightforward, right?
Yeah. Yeah.
Okay, that's the first case. Now let's do the second case. Has much changed? You'll notice that in this case we have two ropes suspending this mass, okay? And let me just point out that they are symmetrical about the center of this mass. I'm going to assume that the mass is equal. It's not some weird mass. It's like heavier on one side than the other. We'll assume that it has a uniform mass. And if you wanted to, you could even consider those two ropes pulling from the same point, but that's conceptually difficult. So we'll just assume that they're separated symmetrically about the center of this thing, but very close together, okay?
Okay.
So we need to draw the free body diagram, right? So we isolate the system again. We're just talking about the mass here, right? So we're going to look at that. And we've got a tension force 1 and a tension force 2 pulling in the upward direction. And we have the weight of the object pulling in the downward direction, right? And that again will be equal to mg. I'll use the same xy coordinate system, so that will be minus mg. And so this time, again, there are no forces in the x direction, so that makes life easy. But in the y direction, we again find that the sum of the forces this time will be T1 plus T2 is equal to plus the weight will be equal to 0 since it's a statics problem, which means that T1 plus T2 equals minus W, which of course is equal to positive mg, just like before. The difference, though, is that this time we have two tensions adding together. And the question is, well, how is the weight distributed over these two lines, these two ropes?
Yes.
Is it equal? If it was equal, that would mean that, T1 could be half an mg and T2 would be another half an mg. So half an mg plus half an mg is, full mg, right? And I would argue at this point that by symmetry, right, it should be equally distributed, okay?
Okay.
So I would say that T1 equals T2, which equals 1/2 mg by symmetry, okay? So now let's look at the most difficult. I'm going to assume that in all of these problems that our xy coordinate system is kind of the standard one like this. That's to the right is the positive x direction and up is the positive y direction. Let's look at the third example. So this time we have to isolate the system, okay? And so we're going to isolate the system. We call it M. We'll again have the weight in the downward direction, but now we have these different tensions. Whether this line here, the one that makes a 30-degree angle to the ceiling, right, this I'm going to call T1. And note that we can break this into its component form as follows. Here I have T1 in the x direction, and here I have T1 in the y direction, right? This angle, so since it makes a 30-degree angle here, this is an alternate interior angle, so this is also 30 degrees, you see?
Yeah.
So T1 in the x direction is going to be equal to, notice it's in the positive direction, so T1 times, anybody? Cosine or sine to get the x component of this tension?
Cosine.
Yeah, T1 times the cosine of 30 degrees. And in the y direction, this tension in the y direction, right, will be T1. Notice going in the positive direction, you can kind of see that, right?
Yes.
Times the sine of 30 degrees. But over here, right, we have T2, right? I'm going to draw a little arrow indicating that this is T2 in the x direction, and that's going to be, what's the angle here? Well, this angle was 60 degrees, right? Because the angle to the ceiling is 60 degrees, which means this alternate interior angle is also 60 degrees, right?
Yes.
So I have to put that into my free body diagram. And so that makes T2 in the x direction equal to, that's a terrible equal sign. I'm trying to make this bigger, but T2 in the x direction is equal to, this time notice that the force is going in the negative direction. So let's go ahead and reflect that in the sign of this by putting negative T2, right, times the cosine of 60 degrees, okay? The y component, however, is in the positive direction still, right? So T2y is equal to positive T2 times the sine of 60 degrees, okay? Now that I have all those components in, I'm ready to solve this thing. So using Newton's second law, this time, since we have contributions in the x and in the y, we're going to consider the sum of the forces in the x and the sum of the forces in the y direction separately. So the sum of the forces in the x direction will be equal to, well, we've got T1x, right, plus T2x, right? Those are the only two forces in the x direction. We've got the x component of the tension from tension 1 and the x component of the tension from tension 2, right?
Yes.
But we've already kind of calculated what those are, and so T1x is equal to T1 times the cosine of 30 degrees, right? And then T2x is minus T2 times the cosine of 60 degrees. And that we know is going to be equal to 0, because this is a statics problem. We're assuming that there's no acceleration, okay, in the x direction or in the y direction, okay?
Okay.
And so this gives us a, a kind of a handy relationship. If we algebraically move, T2 over here, we'll end up getting that T1 is equal to the ratio of the cosine of 60 degrees divided by the cosine of 30 degrees times T2. The sum of the forces in the y direction, well, we've got the y component of the tension from 1, so that's T1y, plus the y component of tension 2, and then plus the weight will be equal to 0. When we have something for those values, we have the T1 y is equal to T1 times the sine of 30 degrees, plus T2y is T2 times the sine of 60 degrees, and then the weight is minus mg, and so this will be equal to mg, right? If I just add to both sides, right? And then we can just algebraically replace T2 or T1 if we want with this algebraic expression, right? So we can substitute in for this, right? So we would get that T1, which is, that's the cosine of 60 degrees divided by the cosine of 30 degrees times the sine of 30 degrees times T2 plus T2 times the sine of 60 degrees is equal to m times g, right? So there's a lot of stuff going on here, so now I guess we need to actually evaluate what these expressions are, right? So that we can solve for T2 here. We're kind of running out of room too. So let's move over here. So what is the, let's just write down right here that the cosine of 30 degrees, which will also be equal to the sine of 60 degrees, as you remember, is equal to square root of 3 over 2, is that right?
Wait, yes? That's right.
And then the cosine of 60 degrees will be equal to the sine of 30 degrees, which is equal to 1/2. Yes?
Yes.
And let's rewrite this expression, T1 sine 30. Well, the sine of 30 is 1/2, so that's 1/2 T1 plus T2 sine 60. Sine 60 is square root of 3 over 2. So that's square root of 3 over 2 T2 equals mg. Okay?
All right.
And then let's substitute in for T1 equals the cosine of 60 over the cosine of 30 T2. So T1 will equal the cosine of 60 degrees is 1/2, right? So that's 1/2. Divided by the cosine of 30 is square root of 3 over 2. Well, that's the same thing as multiplying by 2 over the square root of 3. Canceling those 2's out, times T2, right?
Yes.
So 1/2 times this, right? That's 1 over the square root of 3 T2 plus the square root of 3 over 2 T2 equals mg. All right?
Yes.
Multiply both sides by 2 square root of 3. That gives me 2 square root of 3 mg over here. Gives me T2 here plus 3 T2 here. Right? 1 plus 3 is 4 T2. So I get 4 T2 equals 2 square root of 3 mg, which means that T2 is equal to square root of 3 over 2 m times g. Okay? Now T1, right, then is just equal to 1 over the square root of 3 times T2. So that means that T1 is just equal to 1/2 mg. Okay? So now we've got the tensions for this one. T1 is equal to mg over 2. And T2, the tension in the second line, is equal to the square root of 3 over 2 times mg. Actually, I'll write this as 1/2 times mg. Yeah. So, 3 statics problems. That's how we solve them. The last one obviously being the most complicated one because there's some trigonometry there, but you know it's not that bad in the end. I could have made it a little simpler by substituting in for these cosines and sines earlier on, I think. Yeah, I think that's it. Does that make sense?
Yes.
Okay.